Hello everyone, in this recording we're going to discuss how to visualize trees. So formally, a tree is a special case of a graph where you don't have cycles, so you're not allowed to have a path that loops around and returns back to the source node. This is a very technical definition. I think a more natural way of thinking about trees is thinking of them as hierarchies. So you have like a parent root node, and that node has many children. Each of the children might have its own children nodes, and you have this kind of descending hierarchical structure. So for all of the examples, we're going to be working with a dataset called the FLAIR dataset. So these are the vertices, these are the edges that define the tree structure. FLAIR is a software package, and this is the directory tree structure. So you think of any directory, if you have subdirectories and subdirectories of that defines a tree, right? You have the parent. In this case, like FLAIR is the parent top directory. Analytics is the next directory down inside of FLAIR. Cluster is a directory within analytics. And you have this kind of nested directory structure, and that defines a tree. So these are all the nodes. These are edges. So it's saying there's going to be some other node in here that's going to be called flair.analytics.graph. And there's a link between flair.analytics.graph and the same thing all the way down to link distance. So how do we make it? Using gggraph, we can make a node link diagram using geom edge link for the links and geom node label for the nodes. So label is going to draw the name of the node using the label encoding. Notice I passed in this tree layout, so that's what's going to arrange it in XY position as a tree. And I had the default is just going to be this kind of vertical tree, but then you can specify that you want a circular tree, and it's just going to take the exact same tree and rotate, kind of make it around 360 degrees. So these are both showing the same information, but laid out differently. Okay, so not too hard to make a tree graph using gggraph. What about in D3? So this is going to be a little bit more involved. There are a few main steps. So the first step is when you pass in the data, you'll usually pass it in as two different objects. You'll pass it in as an edge data list and as a node data list. These are each going to be arrays, and each array corresponds to one, or each array element corresponds to one row. But this is not the form that all the D3 tree functions require. So you need to somehow be able to convert that array structure for the edges into some sort of nested, we call it like a stratified JavaScript object. So we're going to be doing this using d3.stratify. We'll see the example below. Once you have a stratified object, you can try getting the XY pixel coordinates for all the nodes in the tree. This is done using the d3.tree function. That's going to figure out the positions of all the nodes. But then if we draw a D3 tree, we usually want to have some sort of smooth path that links the parent and child nodes. This is going to be done using a link generator, or it's a path generator. It's drawing an SVG path, but in a way that's kind of a smooth path, not just like a straight line. We're going to be using d3.linkVertical. Okay, so let's work through the details. This is what the dataset looks like when you just read it in. So it's all the edge information. I'm ignoring the node information for now because we're not actually going to be using any node attributes in our visualization. The d3.stratify function is what's going to convert this array into a nested stratified object. The way it works is this is defining a new function. It's kind of like a path generator, right, or an axis generator. It's something that we can call on other objects, and it will apply. ID is what do you want the node name to be for each node. Parent ID is saying which field contains the information about the parent. Right, so 2 here, this is going to define what that node is, and then the parent of that node is coming from. When you call the stratifier on the original array, it creates this sort of nested data structure. Right? I'm just console logging what happens when I stratify the array that I showed before. So you see this, one of the attributes is children, and it shows this has 10 children. The first of those children has itself 12 children, and it kind of goes on in this kind of nested way. Now, what's really nice is there are lots of helpful functions that can be applied to the stratified object. So here's one example. You can get the descendants by doing .descendants. If I had done .descendants on just the stratified, on the root, it would have given me every single node in my entire tree, right? Because they all are descendants of the root. What I've done here is I've taken the first child node, so it looks at the first level of the tree, all the immediate descendants of the root. I pick the first child, that's the index 0, and I find what are all the nodes that descend from that first child. So this is much smaller. This is only 22 nodes compared to the entire data set. And here we go. This is just showing it's an array where it has the information associated with each of those children. Okay, so that's why it's really helpful to have converted it to a stratified structure. Once we have a stratified structure, we can get the coordinates using this d3.tree function. So what's going on here, I'm saying define a tree layout, figure out a way to lay out the node so that it's shaped like a tree, and make it so that the x length is 600 pixels and the y values go by 350 pixels. It's kind of saying, what do you want, like a very narrow tree? Do you want a very wide tree, tall or short? Right? Now I can apply that generator to the stratified object. And what it does is it's essentially taking the original stratified object and just adding a few extra attributes. Right? So notice we didn't have these x or y before. Right? We had children, data, depth, height, that had all been there. But we didn't have x and y. X and y are new. These are the pixel coordinates that we want to associate with each of these objects. Okay, so that's kind of the trickiest part. Now we can go back to using our standard D3 general update pattern. So here I'm saying append one circle, these are the circles, for every descendant in the tree. So descendants by default on the overall tree is just going to give every single node in the tree because by default tree is just the root node. Right? So it's adding one circle for every node in the tree, and it's putting them at the location given by x and y that were just defined using this tree generator. Okay, so that would just draw the circles in the right locations for a tree. We will also want to have paths that link the parent and children nodes. So we define a link generator. This is d3.linkVertical. It's almost exactly the same syntax as d3.line. Remember, d3.line was defining paths for kind of straight time series lines. LinkVertical is doing it for these kind of smooth links on trees. But it's the same syntax, right? You have a .x, you have a .y that's accessing, and then it's passed into a path, and you set the d attribute in the path, just like when we were drawing time series with d3.line. Okay, and then all of that, you end up getting this kind of tree structure. Right? So the first part was appending the circles. The next part is drawing these link vertical nice paths. Okay, seems like a lot of work. It was definitely more work than just using gggraph, right? But the nice thing is now that we have it all in D3, we can do lots of cool interactivity. So I'm not going to go over the details in these notes, but we'll probably discuss this in class. So I'm able to just hover over different nodes and I see the path, I see all the descendants, I can see all the ancestors very easily, right? And this is actually not too much extra code once we already have the layout and have everything drawn. Also, now you see why I made such a point about wanting to have everything as a stratified object is what I'm doing in this operation. I need to figure out all the ancestors and all the descendants for whatever node I'm currently hovered on. Right? So like, if I go here, I need to figure out that this is the ancestor, that all of these are descendants. Doing that calculation manually would be really tedious. But since it's in a stratified object, we can use the dot ancestors and dot descendants, and it immediately gives us the array with the necessary IDs. Okay, so that is node link diagrams, perhaps the most common way of visualizing tree structures. But they're not the only way. So another very common way of visualizing trees is to use a tree map. So the basic idea is, instead of using lines to indicate parent-child relationships, use enclosure. So say kind of a large glyph is going to represent the parent, and any smaller symbols within that large parent symbol is going to be a child symbol. So this is an example of that, right? These kind of larger groups correspond to like a large directory, right? So you see like there's lots of little small rectangles here, but they all belong to one larger rectangle. So this larger rectangle would be one kind of middle directory in this file system. And then these are all sub-files, or subdirectories within there. Okay. So almost the same kind of syntax, but instead of using, or we're using geom node tile, right? Instead of these edge link and node point, right? And the layout, you have to say, I'm using a tree map layout. Weight equals size is what's saying, I want the leaves, so like the very final directories, to be sized proportionally to how, kind of in this case, it's how large the files are, or how large the directories are. Right. But it's another way of visualizing tree structured data. You can use enclosure. So yes, this is really common when you want to associate some sort of continuous value. So in the file system case, it's like the size of the directories. It's also very often used for budget, right? So if you have the entire US government budget, you could break it down by each of the government departments, and within each of the departments, they might have a lot of sub-agencies, and you could have the size corresponding to the amount of budget for each of those agencies. Okay, so we can do this in D3 using something called d3.treemap. It also operates on a stratified object, right? So everything we said about stratification still applies here. But then when we do the layout step, instead of using d3.tree to build the layout, we use d3.treemap. And it's going to give us x and y coordinates associated with the tree map layout rather than a node link layout. Okay. And then a final example, there's a kind of compromise between a node link diagram and a tree map diagram. This is sometimes called an icicle plot. So here, the y-axis is showing something like the ordinary tree node link diagram, but then the sizes are kind of like in the tree map. Right? So here is like the root node. These are all the descendant nodes, like the immediate children of the root node, and then the sizes of the children correspond to the directory size. And then each of the subdirectories of here are shown as another level, right? And then the sizes are, for that directory, all the subdirectories have their own size. And then you can see all the way deep into the directory system. So it's a kind of a compromise between, this vertical position is a lot like the node link kind of tree, but then the way the spacing works is sort of like a tree map. And of course, you can do this in D3. Instead of using d3.tree or d3.treemap, you use d3.partition, and this will do that layout for an icicle plot. I think this is a kind of cool example. You can zoom in and out, right? And it's just readjusting the layout according to where the user is clicking.